Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this lecture, we will talk about elastic critical moment MCR for unequal end moments. In the previous class, we have learned that M0 critical is equal to pi by L the whole square into EIY into root of IW by IY plus GJL square divided by pi square EIY. This is based on three simple assumptions. One, equal end moments is applied at the central axis of the member. Number two, the beam is simply supported at the ends, which means that the twisting is prevented at supports. The lateral bending or warping is allowed. Number three is that the member is prismatic and it is a doubly symmetric cross sections, as you can see from the picture here. In practice, beams vary from the basic case. There are different types of loading. It can be unequal end moments MA and NB, which leads to a single curvature. It can also be unequal end moments which leads to a double curvature. It can also lead to a concentrated load. It can also have a uniformly distributed load. The loading conditions can also be such that the load is applied at the shear center, which is called as normal condition. The destabilizing condition is the one where the load is applied at the top flange, and the restoring condition can be such that the load is acting at the bottom flange. It is also known as normal condition. In practice, beams are subjected to a variety of loading conditions. So the loading diagram here on the left hand side shows a single curvature, and here the bending moment diagram is given on the right hand side. It can also have a varying moment where MA is greater than MB. It can also have moments acting in the opposite direction, producing a double curvature, and the bending moment diagram is shown on the right hand side. It can also have a concentrated load at midspan. Again the bending moment diagram is shown on the right hand side. The first case has been solved. So we have solved for elastic critical buckling moment MCR when the beam is subjected to equal end moments using differential equation method and energy method. Henceforth, we shall use the energy method for determining MCR. In the upcoming slides, we shall determine MCR for the other loading cases using energy method. Now, the one that is in the box is what we will be seeing in the coming slides. So for a simply supported beam, externally applied end moments of unequal magnitude MA and MB can also be defined as MB equal to psi into MA, where psi equal to MB by MA, where MB is given as the minimum end moment and MA is given as the maximum end moment. So for MB equal to minus M0, MA equal to M0. So we have psi equal to minus 1. So the simply supported loading condition becomes something like this. So we have a uniform bending moment, as you can see here. For MB equal to 0 and MA equal to M0, we have psi equal to 0. So the loading condition becomes M0 on the left hand side and there is no moment applied on the right hand side. So we have a bending moment diagram which is triangular in fashion, as you can see. For MB equal to M0 and MA equal to M0, we have psi equal to plus 1, and this is the loading condition, and we have a reverse curvature, and the bending moment diagram is shown here as plus M0 on the left hand side and minus M0 with a linearly varying moment gradient. Now let us assume that the ends of the member are having the boundary conditions which is restrained against twist gamma equal to 0 and free to warp gamma double dash equal to 0 at both ends. Now let us establish the total potential energy pi of the beam. Consider XYZ be the global coordinate system in undeformed configuration of the beam. Upon application of external end moments MA and MB at shear center, the beam undergoes lateral torsional buckling as shown in figure. Now each cross section in deformed configuration can be defined using three displacement components, that is U, V and gamma, with x dash, y dash, z dash as the local coordinate system. The figure on the right hand side clearly depicts the lateral torsional buckling of the I sections. In the previous problem, we have established the total potential energy pi equal to U plus V of the beam, where the one in the green color is the strain energy of the beam, and the one that is given in the red color is the potential energy of the beam. So the strain energy of the beam U due to three different displacement components U, V and gamma are given here, and the potential energy of the beam V due to equal end moments, that is Mx equal to M0, is shown on the right hand side in red color. So let us look at the potential energy of the beam due to equal end moments. So the potential energy due to in-plane bending is given as V1, and the potential energy due to lateral bending and twisting is given as V2. Now let us look at the total potential energy of the loaded beam with unequal end moments. So we have this equation here. The only change here is in the potential energy of the beam, which is given as mx equal to 0 to L gamma into d square u by dc square into dz. Now let us find out how did we get this equation. Now let us derive the potential energy of the beam due to unequal end moments v. We have the deformed configuration of the structure on the right hand side. So let us view YZ plane towards plus x direction, which is the elevation. When we look at it, we get the buckled shape in the elevation. This is major axis bending curvature V double dash. Now let us look at it from the XY plane towards the positive Z direction, which is the cross section. So we have the gamma, which is the angle of rotation here. And we can see that the displacement is measured as V. Now let us view XZ plane towards the positive Y direction in the plane, which is looking at from the bottom. We have the buckled shape that is given here. So this is minor axis bending curvature minus U double dash. So the corresponding displacement in the x direction is given as U. Using trigonometry, we have tan gamma equal to minus V by U. Here the slope is negative because with the increase in Z, there is a decrease in the slope. For small values of gamma, tan gamma equal to gamma. So minus U tan gamma equal to V, which indicates minus U gamma equal to V. So differentiating twice with respect to Z on both sides gives the equation minus U dash gamma equal to V dash and minus U double dash gamma equal to V double dash. The increment of external work dW external performed as a result of in-plane bending is given as dW external equal to minus mx into d theta x. From slope curvature relationship, we have d theta x by dz equal to d square v by dz square, which implies d theta x equal to d square v by dz square into dz. Substituting the terms in dW external, we have dW external is equal to minus mx into d theta x. So which is given as minus mx into d square v by dz square into dz. From the previous slide, we have the relationship between v double dash and u double dash, which is v double dash equal to gamma into minus u double dash. So now the potential energy of the beam due to mx equal to v into 0 to L dW external into dz, which is equal to minus 0 to L mx into d square v by dz square into dz. When we substitute d square v by dz square equal to minus gamma into d square u by dz square in v, we have the equation v equal to 0 to L mx into gamma into d square u by dz square into dz, which is basically the same as shown in the red color equation, which is the potential energy of the beam due to unequal end moments. Now establishing the total potential energy of the beam. So we have the following terms. The first term can be omitted because the vertical displacement v is very much less than the lateral displacement as well as the rotation gamma. Now after removing it, the potential energy pi of the beam gets reduced. Now certain approximations are made here. The first approximation is u equal to a1 into sin pi z by L plus a2 into sin 2 pi z by L. Here for lateral displacement, we are taking two sine terms. So u is given as a1 into sin pi z by L plus a2 into sin 2 pi z by L. We are taking two terms because here the displacement is not single curvature, it is a double curvature. To approximately capture, we are taking it as two terms. The gamma is given as v into sin pi z by L. Mx is defined as mx equal to m naught into 1 minus 1 plus psi into z by L, where m naught is basically ma. For psi equal to 0, we have mx equal to m naught into 1 minus of 1 plus 0 into z by L. So we have mx equal to m naught into 1 minus z by L. For psi equal to plus 1, we have mx equal to m naught into 1 minus of 1 plus 1 into z by L, which is equal to mx equal to m naught into 1 minus 2z by L. So for psi equal to 1, at z equal to 0, we have plus m naught. Similarly, at z equal to L, we have another plus m naught, which leads to a uniform bending moment diagram. For psi equal to 0, at z equal to 0, we have plus m naught. Whereas z equal to L, we have the bending moment diagram becomes 0. So we have a linearly varying bending moment diagram. So for psi equal to 1, at z equal to 0, we have plus m naught. And at z equal to L, we have minus m naught, leading to a bending moment diagram as shown in the figure. So for the first case, which is m naught critical, we have already derived it. Now we have to look for the other two conditions. So when we have such a condition, for psi equal to minus 1, The simply supported loading conditions are shown here. As you can see, m0 on both sides leading to a single curvature. So for psi equal to 0, we have the loading condition as you can see here, whereas m0 is applied on the left hand side, which is at support A. There is nothing that is applied at support B. For psi equal to plus 1, we have the bending moment diagram which leads to a double curvature. So both sides it is m0. So the first case is derived. Now let us check if these approximations satisfy the boundary condition. So the assumed ends of the members are laterally restrained, which is u equal to 0, free to bend about minor axis, which is u double dash is equal to 0, which indicates my equal to eiy into d square u by dc square, which is equal to 0. The third boundary condition is it is restrained against twist, which is gamma equal to 0, and the fourth boundary condition it is free to warp, which is gamma double dash is equal to 0, which means that m sub f is equal to EIFY into d square gamma by dz square, which is equal to 0. Now let us find the derivatives of u and gamma with respect to z. So we have du by dz equal to u dash equal to a1 into pi by l into cos pi z by l plus a2 into 2 pi by l into cos 2 pi z by l. So when we differentiate it again, we have d square u by dz square equal to u double dash equal to minus a1 into pi by l the whole square into sin pi z by l minus a2 into 2 pi by l the whole square into sin 2 pi z by l. Similarly, d gamma by dz equal to gamma dash equal to b into pi by l into cos pi z by l, and d square gamma by dz square is equal to gamma double dash, which is equal to minus b into pi by l the whole square into sin pi z by l. Right. Now, the first boundary condition u equal to a1 into sin pi z by l plus a2 into sin 2 pi z by l. So when we apply u at z equal to 0, we have a1 into sin 0 plus a2 into sin 0, which is equal to 0. Similarly, u at z equal to l, a1 into sin pi plus a2 into sin 2 pi leads to the value 0. Now let us look at the second boundary condition, which is u double dash free to bend about minor axis, u double dash should be equal to 0. So we have this equation minus a1 into pi by l the whole square into sin pi z by l minus a2 into 2 pi by l the whole square into sin 2 pi z by l. Now let's look at the third boundary condition, which is restrained against a twist gamma equal to 0. So when we substitute gamma at z equal to 0, we get the value 0 because sin 0 is 0. Similarly, gamma at z equal to l, so b into sin pi l by l, which is again 0. Now the fourth boundary condition, it is free to warp, gamma double dash is equal to 0. Again, when we substitute at z equal to 0, we have gamma double dash is equal to 0, and at z equal to l, gamma double dash is also equal to 0. So the boundary conditions are satisfied based on the approximations that we have considered. So boundary condition A, u at z equal to 0, l is equal to 0. Boundary condition B, u double dash at z equal to 0, l is equal to 0. Similarly, boundary condition C, gamma at z equal to 0, l is equal to 0. And boundary condition D, which is gamma double dash z equal to 0, l is equal to 0. Now let us substitute these approximations into the total potential energy equation of the beam pi. So when we get that, we get a long equation here. We can have this split into 4 different integrals, 1, 2, 3 and 4. So derivatives used in the problem is given here, du by dz, d square u by dz square, d gamma by dz and d square gamma by dz square. So let us solve part 1. We have 0 to L half into eiy into d square u by dz square the whole square into dz. So when we substitute it, we get this equation here. So this is of the form a plus b the whole square, which is equal to a square plus b square plus 2ab. So we can expand this equation here, as you can see. After expanding this equation, we can further simplify by taking the square inside each one of the terms. Now we can see that all the constants have been taken outside the integral for each one of these terms. And we also know that the sin square pi z by l is equal to L by 2. Similarly, sin square 2 pi z by L is also L by 2, and 0 to L sin pi z by L into sin 2 pi z by L is equal to 0. These are the integrals that we can understand from the right hand side of the equation. So when we substitute that, we get a much simplified equation here, and this can be further simplified as eiy into pi power 4 by 2l cube into a1 square by 2 plus 8a2 square, which becomes equation 1. And then solving part 2, we have the integral of part 2, which is 0 to L half into Gj into d gamma by dz the whole square into dz. We can again square it, and then we can use the same methodology, which is 0 to L cos square pi z by L is equal to L by 2, using the formulas that are shown on the right hand side. So this gives rise to the simplified form b square into Gj into pi square divided by 4L, which becomes equation 2, and then equation 3 is solving part 3. We have 0 to L half into EIW into d square gamma by dz square the whole square into dz. So we can substitute it, we can simplify it. As you can see, again we can take advantage of the formulas on the right hand side, which is 0 to L sin square pi z by L is equal to L by 2. We substitute that and we simplify this further, which gives rise to the equation EIW into b square into pi power 4 divided by 4L cube. Now let us solve the part 4 of the equation, which is mx into 0 to L gamma into d square u by dz square into dz. Now when we substitute it, we have a big equation here. We can expand this equation here, as you can see, by multiplying both the terms. And after that, we can simplify this further. It's a big long equation. We can simplify this further. This basically is an algebraic manipulation. And we can simplify this furthermore, as you can see here. Now let us substitute the integral values, which is 0 to L sin square pi z by L as L by 2. For a1b and for a2b, we have 0 to L sin pi z by L into sin 2 pi z by L, which is equal to 0. And then the third term is a1b, which is 0 to L z into sin square pi z by L into dz, which is given as L square by 4. And the fourth term, which is for a to b, we have 0 to L z into sin pi z by L into sin 2 pi z by L, which is given as 8 L square by 9 pi square. So when we substitute all those terms, we can simplify this further. And as you can see here, it gets further simplified and it becomes equation 4, which is minus m naught into a1b into pi square into 1 minus psi by 4L minus a2b into 32 into 1 plus psi by 9L, which is equation 4. Now substituting 1, 2, 3 and 4 into pi. So when we do so, we get a large equation here. Now the total potential energy equation of the beam has been obtained. Now using the principle of stationary total potential energy, we have for equilibrium the total potential energy of the system pi should be equal to 0, which means that del pi should be equal to 0. So the critical moment is reached when the neutral equilibrium is possible. The requirement for neutral equilibrium is that the partial derivative of pi with respect to a1, a2 and b should vanish. Here in this equation, we have three constants. One is a1, another is a2 and another is b. So when we partially differentiate with respect to a1, we get one equation. When we partially differentiate with respect to a2, we have another equation. And when we partially differentiate with b, we have the third equation. So applying partial derivative to pi with respect to a1, we get this equation here. Again, this can be much simplified further, which is given as eiy into pi power 4 divided by 2L cube into a1 minus m naught into 1 minus psi into pi square by 4L into b, which is equal to 0 is the equation 5. Applying partial derivative to pi with respect to a2, we have again a big equation here. We can simplify this further. After simplification, we get a very nice equation here, which is 8 into eiy into pi power 4 divided by L cube into a2 plus m naught into 32 by 9 into 1 plus psi by L bracket close into b is equal to 0. So this becomes equation 6. Now let us apply the partial derivative of pi with respect to b. When we do so, we get a big equation. Again, this can be further simplified. So when we simplify this further, we have equation 7, which is minus m naught into pi square by 4L into 1 minus psi into a1 plus m naught into 32 by 9 into 1 plus psi by L into a2 plus gj pi square by 2L plus eiw pi power 4 by 2L cube into b is equal to 0. Now we have three equations, 5, 6 and 7, which can be represented in the form of a matrix. So we have a1, a2 and b. So when we represent it, we get this in the form of a matrix. And for a non-trivial solution, the determinant of the matrix should be equal to 0. So when we expand the matrix, we have the determinant of the matrix is given here, and it's a long big equation, as you can see at the bottom. Again, this can be further expanded, and we simplify this further by doing a lot of algebraic manipulation. So here we are dividing with pi power 4 EIY by L cube on both sides. When we do so, we get a much simplified equation. As you can see here, now we multiply by 2 on the both sides. We get another simplified equation. We can further simplify by dividing with 4 pi power 4 by L square on both sides. We can cancel the terms, and then it leads to much more simplification. And finally, we have on the left hand side EIY into pi square by L square into GJ plus EIW into pi square by L square, which is given us on the right hand side 0.032 into 1 plus psi the whole square into m naught square critical plus 0.25 into m naught square critical minus 1 minus psi the whole square. So we apply square root on both sides. We can see that the root of pi square EIY by L square into pi square EIW by L square plus GJ is m naught critical for equal n moments, and it is equal to m naught into root of 0.032 into 1 plus psi the whole square plus 0.25 into 1 minus psi the whole square. So we have m naught by m naught critical is given by this equation. So this is equal to C sub B, which is the lateral torsional buckling modification factor as per AISC. And C sub B is given as root of 1 by 0.32 into 1 plus psi the whole square plus 0.25 into 1 minus psi the whole square. So this m naught by m critical equal to C sub B, and C sub B equal to 0.282 minus 0.436 into psi plus 0.282 into psi square power minus half. So this provides a close match with CB adopted by AISC in 1961. So the general provisions of AISC is given on the left hand side. So the C sub B as per AISC is equal to 1.75 plus 1.05 into psi plus 0.3 into psi square, which should be less than or equal to 2.3. This was adopted by AISC in 1961 till 1986. So when we plot 1 by C sub B with respect to psi, we get two curves. The one with green color is the AISC and the one with red color is the theoretical value that we have derived from the equations. So it is a very close match. Note the above equation is applicable only to moment diagrams that consist of straight lines alone. So this is an assumption that has been made in the derivation of C sub B, so that has to be taken into consideration. Now let us look at the application of CB for a given moment diagram. So m naught is the applied moment on the left hand side and psi into m naught is the applied moment on the right hand side, where psi is given as minimum end moment divided by maximum end moment. So the C sub B equal to 1.75 plus 1.05 into psi plus 0.3 psi square less than or equal to 2.3. So m naught by m critical equal to C sub B. So mx is given as m naught into 1 minus of 1 plus psi into z by L. We should note that this solution is specific to the direction of the moment assumed in the derivation. So for equal n moments, psi equal to minus 1 and the bending moment diagram is given here. So when we substitute the value of psi equal to minus 1, we can find out the lateral torsional buckling modification factor C sub B, which is given as 1.75 plus 1.05 into minus 1 plus 0.3 into minus 1 the whole square, and C sub B is given as 1.0, which is less than or equal to 2.3. When we plot it, we get on the top 1 by C sub B equal to 1, as you can see here. So the elastic critical moment MCR for psi equal to minus 1 is given as m naught by m naught critical equal to C sub B. So m critical equal to CB into m naught critical. So which means that it is equal to 1.0 into pi square EIY divided by LLT the whole square into root of IW by IY plus GIT into LLT the whole square divided by pi square into EIY. So m critical for equal end moments, this is the equation. Now for equal and opposite end moments, we have psi equal to plus 1. So finding the lateral torsional buckling modification factor C sub B, we have C sub B is given here. So when we substitute plus 1, we have C sub B equal to 3.1, which should be less than or equal to 2.3. So we have on the right hand side the value of 1 by C sub B plotted. So for elastic critical moment MCR for psi equal to 1, we have MCR by m naught critical equal to C sub B. So m critical equal to CB into m naught critical, which is equal to 2.3 into m naught critical equation that we previously described. Now let us compare C sub B in AISC 360 with M in BS 5950. So M naught by M critical equal to C sub B in AISC 360, where C sub B is given as 1.75 plus 1.05 psi plus 0.3 psi square, which should be less than or equal to 2.3, adopted by AISC in 1961 till 1986. However, in BS 5950, we have the equation reversed. We have M naught critical by M naught is equal to M. So M equal to 0.57 plus 0.33 beta plus 0.1 beta square, which should be greater than or equal to 0.43. So this is table 18 in page 31 of section 4 of BS 5950 part 1 1990. We can see that the term M is defined as equivalent uniform moment factor. So for equal and opposite end moments, we have beta equal to -1. So finding the equivalent uniform moment factor M, we have M equal to 0.57 plus 0.33 into beta plus 0.1 into beta square. Now when we substitute the value of beta equal to -1, we get M equal to 0.57 plus 0.33 into -1 plus 0.1 into -1 square. We get the value of 0.34, but however this value should not be less than 0.43, as you can see from the left hand side highlighted in green color as per the code BS 5950. So the elastic critical moment MCR for beta equal to -1 is given as M naught critical by M naught equal to M. So M critical is equal to 1 by M into M naught critical. So we have M critical equal to 1 by 0.43 into root of pi square EIY by L square into pi square EIW by L square plus GJ. So we have the equation here, M critical equal to 2.32 into pi square into EIY divided by LLT the whole square into root of IW by IY plus GIT into LLT the whole square divided by pi square EIY. This is the same equation that we get in AISC 360 also, as demonstrated here. With this one, we have been able to successfully use energy method to solve the equation for moments that are not equal on both sides, and hence we were able to achieve the factor which is known as equivalent uniform moment factor M as per BS 5950, or we can also call it as lateral torsional buckling modification factor C sub B as per AISC. So thank you very much, and I look forward to meeting you in the next class.